In this lesson, we're going to talk about the standard normal curve. But first off, we need to talk a little bit about the normal distribution. In previous sections, we distinguished the difference between discrete and continuous random variables. And we talked about that continuous random variables have an infinite number of possible values that can be represented on a particular interval. And then we described that as not being able to count it. Whereas discrete random variables, you are able to count them. Well, when we talk about a normal distribution, that is going to represent a continuous probability distribution. So in this section, we're going to talk about the normal distribution and really focus on that, and then we're going to build up to what the standard normal distribution is. So the first thing that you need to know when we're talking about the normal distribution is we need to know the properties and understand what those are so that we can identify when we come into a normal distribution what that is. Okay, a normal distribution, we already said that's a continuous probability distribution for a random variable. The graph of a normal distribution is called a normal curve, and you typically think of the normal curve as that bell-shaped curve that looks like this. It has a bell shape, or sometimes you'll hear it called mound-shaped and symmetric. And there's some other words that you can use to describe it, one peak and symmetric. But basically, you're going to have that kind of a curve where most of it is going to occur in the center at one peak, and then it's going to be symmetric and then tailor off on either end. Okay, now the second thing you need to know is that the mean, the median, and the mode of a normal distribution are all going to be equal. And that is due to the fact that it's symmetric. Okay, the next thing that you should be aware of for the properties is that the total area under the curve, which represents the probability of something happening, that's going to be equal to 1. Or if you're talking in terms of percent, that's going to be 100%. So the total area under the curve represents probability and is equal to 1 or 100% depending on how you're presenting the information. Okay, another thing that you need to know about the normal distribution is that when you look at the tails and they go off to the end, so by tails, I mean this piece over here when it comes off to the end. Okay, the tails, it gets closer and closer to the x-axis, but theoretically, as it gets farther away from the mean, it's never actually going to touch the x-axis. Sometimes when we draw things by hand, it's hard, to make sure it's perfectly symmetric and things like that. And sometimes I might get sloppy and the curve might come down and touch the x-axis. But understand that theoretically, the curve is never going to actually touch the x-axis. It's just going to have that idea that it's going to get closer and closer and closer to the x-axis, but it's never going to actually touch it. Okay, and then the next thing is that the mean will be in the center. And when you're talking about the population mean, we'll call it mu, as you come out in either direction, 1 standard deviation or 2 standard deviations, you're going to take m plus your standard deviation, or I'll put down here minus, as you come further and further out from the mean. So here's the mean, and as you come out this way, this value here will be the mean plus your standard deviation. If you come out again another standard deviation, this will be the mean plus 2 standard deviations. And then if you come out in this direction, you'll be subtracting your standard deviations. Now, you can identify approximately where the first standard deviation should come out when you look at the normal curve. When you look at that curve, this right here is called the point of inflection. And that's the point on the graph where the graph goes from concave down, which looks like it's facing down, to concave up, where it looks like it's facing up. Okay, and when you find, and you just do a quick approximation of where you think that point of inflection is, that's approximately where you should come down and where that first standard deviation should start. So let's put that also under here. So the mean is going to be in the center, and as you come out, you're going to add and subtract standard deviations, and then the point of inflection will be approximately where the first standard deviation should be marked on the axis. Okay, so those are some basic properties of your normal distribution. Okay, now that we have an idea of what a normal distribution is and what it looks like, now we're going to discuss the difference between the normal and the standard normal distribution. Now, if I gave you a normal distribution, let's say we are talking about some scores on a test. Let's say that the mean is 100, and let's say that the standard deviation is 5. So that means, looking at my graph here, it looks like this is the part that's concave down, and it looks like this is the part that's concave up. So I'm going to estimate that about right here is where my first standard deviation will come out. So this will be 105, because when I add it from here to here, I keep adding 5 because my standard deviation is 5. So then I have 110 here. When I come out, another standard deviation, and then I have 115. And then going in the other direction, if I go one standard deviation to the left, that's going to give me 95, then 90, and then 85. These are what's called our values of x, which is our raw scores. That's another way of describing it, or our raw data. Okay, now, when we standardize something, we're not looking at the raw data. We're actually looking at how far away the values are from the center, the mean, based on the number of standard deviations. So when we're looking at the standard normal distribution, this curve is going to be always the same, because with the standard normal curve, because we're talking about the distance away from the mean based on standard deviation, that means the center is always going to be 0, because you're 0 standard deviations away from the mean when you're sitting in the center. Then this will always be 1 when I'm 1 standard deviation out. This will always be 2. This will always be -1. This will always be -2, etc. Okay, so these values here are always going to be 0, 1, 2, 3, or -1, 2, 3. Now these values here, when we're looking at the standard normal curve, these are called our z-scores. And those z-scores represent how far away we are from the mean in terms of standard deviation. So, for example, if I wanted to compare my value of x in the normal distribution to the value of z in my standard normal distribution, if I was looking at a score of 110, that would be equivalent to a z of 2, because 110 is 2 standard deviations from the mean. Let's say I was looking at a value of 106, and I wanted to know how far away I am from the mean in terms of standard deviations. I would know it would be a little bit more than 1, because I know 105 is 1 standard deviation away from the mean. But is it 1.2? Is it 1.3? We don't know. There's a formula for that. To find your value of z, whether it's a whole number or something in between, you take your raw score, your value of x, you subtract your mean, and you divide by your standard deviation. So in this case, if I want to find the corresponding value of z for 106, I would take 106, which is my value of x, I would subtract my mean, which is 100, and I would divide by my standard deviation, which is 5. So I would get 6 over 5, which would be 1.2. Let's say I wanted to look at what happens on the other side of the mean. Let's say I wanted to see what happens when x is 94. At 95, we know that's a standard deviation of -1 away from the mean, meaning I'm 1 standard deviation to the left of the mean or below the mean. So I should be -1 point something between -1 and -2 when x is 94. So if we do that again for x is 94, let me erase, and we're going to do it again. Now, if I put in x is 94, I take 94 minus 100. That gives me a -6 over 5, which is a -1.2. Okay, we're going to go through an example now using some new notation. You'll see this new notation right here. The x is the variable. The n means it's normally distributed, meaning it has that bell-shaped curve. The first number after the n in the parentheses represents the mean. So in this case, it means the mean is 5. And the second number in the parentheses is your standard deviation, which in this case is 6. Now, the book uses the actual symbols. I use SD for standard deviation. We should start using these symbols now that we're going to have to start identifying the difference between population and sample, standard deviation, and mean. So this is going to be your mu, and then your standard deviation is your lowercase sigma. Okay, now it says we're going to suppose that x is 17 and we're going to figure out what z is. All right, so let's just, for the sake of practicing, let's look at our curve. Your mean always goes in the center. So my mean is 5. My standard deviation is 6, which means approximately where my curve goes from concave down to concave up, which I'm imagining is about right here. That means that's where my first standard deviation is going to be. Okay, here's my graph. So now every one of those tick marks represent a standard deviation, which means when I go to the right, I'm going to be adding 6, and when I go to the left, I'm going to be subtracting 6. So if I add 6, this is going to be 11. If I add 6 again, that's going to be 17. And if I add 6 again, that is going to be 23. Now, we're specifically looking for x is 17, so I'm not going to bother going out to the left. But if you did, remember you subtract 6 going this way. When we think about it in terms of the standard normal curve, remember the standard normal curve shows us how far away from the mean we are in terms of standard deviation. So the mean, when you're looking at the standard normal curve, will be 0. Coming out this way, this would be 1, this would be 2, this would be 3. So these are my z's, and that's for your standard normal curve. And then if I come out this way, I would have these. -1, -2, -3. Now it's asking us to find the value of z when x is 17, and that is right on a whole number, right on our graph for one of our values of z. So we can see that when x, our raw data is 17, our value of z is 2, which means we are 2 standard deviations to the right of the mean because it's a positive 2. Now, if it wasn't something that we could visually check on our graph and it was something in between one of our whole numbers, then remember we have this formula, z equals x minus the mean, which is our mu, divided by our standard deviation. So I would put in my raw score of 17, I subtract my mean, which is 5, and I divide by my standard deviation, which is 6. So I would get 17 minus 5, which is 12 over 6, and we get 2, which checks out when we check it visually on the graph. In this next example, we have that some doctors believe that a person can lose 5 pounds on average in a month by reducing his or her fat intake and by exercising consistently. Suppose weight loss has a normal distribution. We're going to let X be the amount of the weight loss, so that's our variable in pounds, and it says the amount of weight loss in a month, and we're going to use the standard deviation of 2 pounds. And so here's our notation. X is our variable, N is for the fact that this is a normal distribution, 5 is our mean, and 2 is our standard deviation. So when we draw a quick sketch of what this looks like, here's 5, which is my mean in the middle. My standard deviation means every time I come out one more standard deviation, that's 2 more pounds. So going in this direction, I'm adding 2 pounds. Going in this direction, I'm subtracting 2 pounds. Okay, now let's use this graph to answer our questions. Suppose a person lost 10 pounds in 1 month. We're going to find the z-score when x is 10. So if I have x is 10, that's right here somewhere. So I know that when I'm sitting on the mean, thinking about standardizing this, so here are our x's, our z's are going to be our standardized values. So this is 0 standard deviations away from the mean. This is 1, this is 2, this is 3. This is -1, meaning 1 standard deviation but to the left. This is -2, and this is -3. So when I look at where x is equal to 10, I'm envisioning that that should be somewhere between 2 and 3 standard deviations away from the mean. And it should be positive because I'm on the right-hand side of the mean or above the mean. So if I come out with an answer that's like 3 point something or -2, like I'll be able to tell right away that I did something wrong because I know it should come out somewhere between 2 and 3. So I'm going to use my formula, z is equal to x minus the mean divided by my standard deviation. I'm going to take my x, which is 10. I'm going to subtract my mean, which is 5. And then I'm going to divide by my standard deviation, which is 2. So that gives me 5 over 2, which is 2.5. That's my value of z. So this is telling me that I'm 2.5 standard deviations away from the mean, above or to the right of the mean, which is exactly where we see this on our graph. We can visually check it. Okay, looking at the next example, it says suppose a person gained 3 pounds. What is z and x? X, if you gain 3 pounds, you're doing the opposite of losing. In this example, losing weight is positive, right? If I have 5 pounds, that means I'm losing 5 pounds. So we need to do the opposite. Now I want to find my corresponding value of z. So if I look at where -3 is on my graph, right, if I come out, every time I come this way, I'm subtracting 2 because 2 is my standard deviation. That's actually going to lie exactly on a value of z that is -4. So that is a z of -4. Now, if that wasn't easy to see on our graph, then remember you can always use your formula. I have my x minus my mean all over my standard deviation. My x is -3. I'm going to subtract my mean, which is 5, over my standard deviation, which is 2. That gives me a -8, because I have a -3 minus 5, and then over 2, so that gives me a z of -4. In this example, it says the mean height of 15 to 18-year-old males from Chile from 2009 to 2010 was 170 centimeters and a standard deviation of 6.28. Male heights are known to follow a normal distribution. We're going to let x be our variable, which represents the height. And then we have our notation here that we're getting familiar with. The x is our variable. The n means this is a normal distribution. And then this first number is the mean, and the second number is our standard deviation. Okay, so let's use this information to draw a quick sketch of our normal curve. So the mean always goes in the center. This represents centimeters in height. Okay, so if I come out from 170 in the center, if I add 6.28, that's coming out 1 standard deviation, so I'm going to label that as 1 SD. If I come out again 6.28, that's going to give me 182.56. And then if I come out one more time, that's going to give me 188.84. So this is coming out 2 standard deviations, and this is coming out 3 standard deviations. Now, if I come out to the left, let's see, if I come out and subtract 6.28, that's going to give me 163.72, then 157.44, and then 151.16. Now, as I come out each standard deviation going to the left, because I was subtracting my standard deviation, I'm going to label this as -1 SD, -2 SD, and -3 SD. And now we can use this to help us answer these questions. So let's see, it says, suppose a 15 to 18-year-old male from Chile was 168 centimeters tall. We want to find the value of Z when he is 168 centimeters tall. That's going to be really close to 170, but on this side of 170. So I'm expecting that my value of Z should come out negative. So using our formula, my x, which is my data value, that's 168, minus my mean over my standard deviation. When you put that in on the calculator, you should get -0.32. Because it's negative, we know that it's on the left side of the mean. And the 0.32 means that it's 0.32 standard deviations from the mean. Okay, let's look at part B. Part B says, suppose that the height of a 15 to 18-year-old male has a z-score of 1.27. What is the male's height? So now this is a little bit different because we got to work backwards. We can still use our formula, but now we have to look at it in a different way. Since I want to figure out what my value of x is, and I know everything else, what I'm going to do is I'm going to solve this equation for x. So I'm going to multiply both sides of my equation by my standard deviation, and that will allow us to cross that off. So now I'll have z times my standard deviation is equal to x minus mu. So now to get x by itself, I have to just add mu to both sides. So my value of x is going to be whatever I get when I take z times my standard deviation and I add my mu. So this is the formula you want to use when you are looking for x and you know the value of z. We're really just using the same formula. We're just using it backwards. Okay, so if I want to find the value of x, I need to take my value of z, which is 1.27, multiply it by my standard deviation, which is 6.28, and then add my value of my mean, which is 170. Okay, now if I put that in on my calculator, I am going to get 177.98. So if a guy that is age 15 to 18 from Chile has a height that is 1.27 standard deviations above the mean, that means his height is actually 177.98 centimeters. So if we come up here and look at it on the chart, I'll use purple for this one. If we look for 177.98, that's going to be somewhere around here. And if you notice, it's between 1 and 2 standard deviations above the mean, and that's why z is positive. And so z was given to us as 1.27. So when x is our raw data is 177.98 centimeters, that means z is 1.27, which tells us a little bit more than 1 standard deviation above the mean. Okay, now we're going to go into more depth with the empirical rule. In previous section, we already started talking about it a little bit, but now we're going to go into it in a lot more depth. And the empirical rule, you might also see it known as the 68, 95, 99.7 rule. That's another way to say it. It just depends on what book you're looking at. And what the empirical rule tells us is that 68%, and this is, I should stress that this is approximately 68% of the data values lie between z equals -1 and z equals +1, meaning 1 standard deviation out in either direction of the mean. Then we could say approximately 95% of the data lie between z equals -2 and z equals +2. So if you go out 2 standard deviations out on either side of the mean, 95% of the data is going to fall in that area. And then lastly, if we go out 1 more standard deviation, about 99.7% of the data is going to lie between z equals -3 and z equals 3. Okay, so now looking at this, we're going to break this down a little bit more. So in here, let me actually use the highlighter. So in the area where we have between -1 and 1 for z, that is going to be 68% of the data. Now if we want to break it up into smaller chunks so that we can get some more detail, if I want to know what is specifically just from here to here and here to here, how much data falls just 1 standard deviation out from the mean and just half of that, then I would take 68 and divide it by 2. And we can do that specifically because this distribution is symmetric. So I know the area under the curve is going to be even on either side of the mean. So I know it's going to be half of 68. I'm going to say that from here to here is 34% of the data. And then from here to here is 34% of the data. So that the total from here to here is 68% of the data. I would subtract off that 68% in the middle to see what total is left in the green area, and that would give me a total of 27. So I know the total of those two green areas is 27. But if I want to know what goes in each of those green areas, then I have to take 27 and divide by 2. So when I do that, I get 13.5. So I know that all the way from here to here is 95% of the data. But we just used some common sense and some arithmetic to figure out that from here to here is 13.5%. And from here to here is 13.5%. I know that all of this, everything under the curve from here to here, covers 99.7%, everything under the curve from here to here. But we know that from here to here is 95%. So if I want to see what is in just these yellow strips right here, I'm going to take 99.7 and I'm going to subtract 95. So I know a total of 4.7 is in both of those yellow strips. So if I want to see what is in just one of those yellow strips, I divide by 2. And so I know that just in this yellow strip here, I have 2.35% of the data. And in this yellow strip here, I have 2.35% of the data. Okay, now to take care of these last little pieces here, these wings, I know that from here to here is 99.7% of the data. I know that under the entire curve is 100% of the data. So what's left in these tiny little pieces, or these little wings off to the right and to the left, I know is 0.3% in total for both of them. Then if I want to know what's in each one, I divide by 2. So in this little wing right here, that's going to be 0.15% of the data. And in this little wing right here, that's going to be 0.15% of the data. The total of everything under this curve should add to 100%. And now we can check it. If I add 0.15 and then I add this area here, which is 2.35, and this area here, which is 2.35. Then if I add this area here, which is 13.5, and this area here, which is 13.5, and then I add this area here, which is 34, this area here, which is 34. If you add all of those up, you should get 100% of the data. Okay, now let's use this to answer these questions below. In the first example, it says, suppose X has a normal distribution with a mean of 50 and a standard deviation of 6. Let's draw our picture here. Now, if I wanted to write out the notation, it would look like this. Because it's a normal distribution, I would have the mean is 50 and a standard deviation of 6. 50 is going to go in the middle, and then I'm going to keep adding or subtracting 6 to come out in either direction. So this would be 56. This would be 62. This would be 68. That's 3 standard deviations out. So these are my x's. If we're looking at our standard normal curve and we're thinking about z's, this would be 0, 1, 2, and 3. Now coming out this way, my x's, if I subtract 6, that's going to give me a 44. If I subtract 6 again, that's going to give me a 38. And then one more time, that's going to give me a 32. Now, if I think about it in terms of standard scores or my z values, this would be -1, -2, and -3. Now, so what this tells me is we can interpret it like this. Approximately 68% of the data is going to lie between 44 and 56. Because if we scroll back up here and we look at our empirical rule, we said that 68% of the data comes one standard deviation out in either direction. So that's this from here to here, 68%. Now, if I go out another standard deviation from here to here, that's 95% of the data. So I can say approximately 95% of the data lies between 38 and 62, because now we're coming out 2 standard deviations in either direction. Now, if we look at this last one, if we come all the way out this way to 3 standard deviation, that's 99.7% of the data. So I can say approximately 99.7% of the data lies between that's 32 and 68. So that's how we can use the empirical rule to interpret some of this information. In this last example, we are going to look at the heights of men again. We have a normal distribution. The mean is 172.36 centimeters, and the standard deviation is 6.34. Notice they're labeling this a different variable this time, which is totally fine. You just have to keep track of it. All right, so let's make our picture so that we can visually see what's going on here. We have the mean in the center as 172.36. And then every time I come out a standard deviation, that's going to be 6.34. So let's see. If I come out 6.34, that's going to be 178.7. If I come out another 6.34, that's going to be 185.04. And then one more time, that would give me 191.38. Now going in the other direction, I'm going to subtract 6.34. And that's going to give me 166.02. Then 159.68. And then 153.34. Now, using our chart from the empirical rule, I know that this represents 34% of the data. This represents 34% of the data. So for the total purple area, that's going to be 68. Then I know this is going to be 13.5%. And this is going to be 13.5%. And then if we go out again, that's going to give me this area, which is 2.35%. And this is 2.35%. And then out one more time, this little tiny area right here we said was 0.15%. And this little tiny area here was 0.15%. So now we can use this chart to answer our questions. It says about 68% of the y values lie between what two values? So we know that 68 would be between here and here. So I would say that it lies between 166.02 to 170, to 178.7 centimeters. So 68% of men approximately are between these two heights. Okay, now 95% of the y values lie between what two values? Well, 95 we know goes out 2 standard deviations, and we know that we can check it by adding it up. If I take 13.5 plus 34 plus 34 plus 13.5, that gives me 95. And so I know that approximately 95% of men have a height between 159.68 and 185.04 centimeters. So that's between here and here. Same thing now, we're going to go out one more standard deviation in either direction. It says about 99.7% of the y values lie between what two values? Now we're going out to 3 standard deviations, so that would be between 153.34 and 191.38 centimeters. Now, looking at these, now we're going in reverse where they're giving us the heights and we got to figure out the percentages. So this says about what percentage of values lie above 159.68. So if we're looking at all the values that lie above 159.68, here's 159.68. We're looking at everything that falls in this category. So I would have to take all of those percentages and add them up to double check. So I would have to take all of those percentages and add up to find out. So I would take 13.5 plus 34 plus 34 plus 13.5 plus 2.35 plus 0.15. That would give me 97.5%. Okay, now the next one. It says about what percentage of values lie below 159. So below 159.6a is this area that I just highlighted in green again, going in the other direction. There's 2 ways that we can do this. I know that the full graph contains 100%, so I could take 100% minus what lies above, which is 97.5, and I would get 2.5%. Or the other way I could do it is just add up the 2 slices of that graph, which is 0.15 and 2.35, which again gives me 2.5. So either way, it's fine. The next question says, what percentage of values lie above 191.38? So here's 191.38 that I just highlighted in green. That's just this little piece right here. So that's just 0.15% of the data. Last question, about what percentage of values lies between 159.68 and 166.02? Well, if I look at those values, I'm going to highlight them in green. So 159.68 is here. 166.02 is right here. So that is just this area right here, which is 13.5. So this graph that we just made together with all the sections built in of all the percentages, it's really important that you keep that handy. Now, I wrote in our specific values that go along with this example. However, if you look up here, we have a general form of that graph right here, where it just shows you based on the standard deviations. So I would definitely keep that handy when you're working on these questions.